In this class, we will deal with intrinsic semiconductors. Semiconductors in its pure state is what is meant by intrinsic semiconductor. So, the examples for intrinsic semiconductors are silicon and germanium. So, let us study the structure of silicon and let us discuss the lattice structure of silicon. Silicon having an atomic number 14. So you know that the nucleus of silicon with the 14 protons surrounded by electrons with configuration 284. So here 2 electrons in the first shell, then 8 electrons in the second shell, then 4 electrons in the final shell. So, in electronics, we don't draw this much when we draw a silicon. What we are doing is that we just incorporate the first 2 shells to the nucleus. So, we are adding 8 plus 2, 10 electrons to this nucleus. So how will the charge get represented? It is plus 14 of the nuclear charge minus 10. So you will get an atomic core of charge plus 4. So 2 electrons plus 8 electrons, that is 10 electrons carrying minus 10. Then there is a charge of plus 14. So plus 14 minus 10, it is plus 4. So we are squeezing the first and the second shell to the nucleus such that we call it as an atomic core with a charge of plus 4. So what is remaining is the 4 electrons. So every silicon atomic core is represented by plus 4 and they are having 4 electrons surrounding it. And these 4 electrons are used for covalent bonds with the adjacent silicon atoms. So when we focus on a silicon atomic core, the 1 electron will get bonded here, and the 1 electron of this also get bonded. Like that, we will get a never-ending structure like this. Every atom is bonded to every other atom so that the intrinsic semiconductor solid is produced and it is a never-ending structure. So let us focus on this silicon atom where the atomic core is plus 4, its 4 electrons are getting bonded to 4 neighboring silicon. So what happens is that less than 0 Kelvin, what is it? Less than 0 Kelvin, no electrons in these bonds are able to come out. So what is it? An intrinsic semiconductor less than 0 Kelvin, they are not having any charge carriers. So you may note the point that an intrinsic semiconductor less than 0 Kelvin will act as an insulator as there are no charge carriers for them. So a question can be asked to you, what is the nature of intrinsic semiconductor less than 0 Kelvin? What is your answer? The intrinsic semiconductor less than 0 Kelvin will act as an insulator. So they will act as an insulator. So what happens when it is greater than 0 Kelvin? So greater than 0 Kelvin, what happens is that some electrons gain their energy. So what happens is that they leave this bond. But when they leave the bond to the interatomic spaces, there is a vacancy of electron produced here inside these structures. So every electron moving out will create a vacancy. This vacancy of an electron is called a hole, and as it is a vacancy, it is positively charged. So electron is negatively charged. The vacancy of an electron is a hole which is positively charged. So which are the charge carriers in an intrinsic semiconductor greater than 0 Kelvin? In an intrinsic semiconductor greater than 0 Kelvin, the charge carriers are electrons and holes. So holes are vacancies of electrons. So the electron as well as holes contribute current when it is greater than 0 Kelvin in an intrinsic semiconductor. So a question comes to you. What is the ratio of charge carriers in an intrinsic semiconductor? So what is the ratio of electrons to the holes in an intrinsic semiconductor greater than 0 Kelvin? Wherever an electron is escaping, a hole is produced. So the ratio of charge carriers in an intrinsic semiconductor greater than 0 Kelvin, or the electron to hole ratio, is 1:1. Now, let us discuss about the total current in an intrinsic semiconductor greater than 0 Kelvin. Since we have discussed the electrons and the holes both contribute equally because they are equal in number. So, the total current I in an intrinsic semiconductor greater than 0 Kelvin will be the electronic current plus the hole current. The total current is contributed by electronic current and hole current. Now, let us deal the band theory of an intrinsic semiconductor. So, what is it? There is a valence band, there is a conduction band. You have already studied in the previous classes. There is a valence band here. The valence band can be drawn like this with the lower energy level, and the conduction band is here, and we have to draw the increasing energies. So valence band, conduction band, you know that there is an energy gap in between which is called the forbidden energy gap. So what happens when we draw in an intrinsic semiconductor less than 0 Kelvin? Do they have some electrons for conduction? No, the electrons were not able to escape as it is less than 0 Kelvin. So all the electrons inside the valence band will remain as such. So many electrons are there. All the electrons, we can draw it like this with no electrons in the conduction band. So this is the band gap diagram for an intrinsic semiconductor less than 0 Kelvin. You can refer to your textbook for this diagram. Next, what happens when an intrinsic semiconductor is having a temperature greater than 0 Kelvin? I have already told you that the electrons will jump from these bonds, creating the holes, right? So now they are ready for conduction. So moving back to the energy band diagram, some of the electrons can jump to the conduction band. So now we are going to draw intrinsic semiconductor greater than 0 Kelvin, where we may say that some 3 electrons we marked here because they have been escaping from the bonds and going out and ready for conduction. So if 3 electrons are there in the conduction band, you have to draw equivalent number of holes. So this is represented by a hole, and a full circle shaded can be represented as an electron. So this is an intrinsic semiconductor greater than 0 Kelvin, where you can show some electrons in the conduction band because they already is contributing conduction, but the equal number of holes should be drawn in the valence band. You may please note it. Some children may randomly draw some 8 here, some 4 here, like that. No, how many number of electrons are there in the conduction band? Equal number of holes should be drawn here. So when an intrinsic semiconductor less than 0 Kelvin, no electrons in the conduction band, all the electrons are accommodated in the valence band, and there is no hole in the valence band. But intrinsic semiconductor greater than 0 Kelvin, what happens is that some of the electrons can conduct. So show those electrons in the conduction band, the equal number of holes in the valence band.